Open source. Hello, everybody. I'm Nadya. I'm going to start. I'm a professor at the University of Washington. I run a group called Machine Agency. This talk is about things that we do in Machine Agency, which largely have to do with building toolkits that support people who want to automate different kinds of processes. Hannah is also here. Hannah's from Machine Agency. I'll talk more about Hannah later. All right, so my background is machine building. I used to build a lot of machines, especially was interested in making machines that could be made on other machines. So here's a series of milling machines that can be made on other milling machines that were also replicated by other people. We use these to mill PCBs. At a prior teardown, I talked about milling PCBs, and lots of people were against it. But actually, it's a fun prototyping method, great for single-sided PCBs. We also, together with Alon Moyer, I made PopFab, a relatively old project where you could do tool changing. So this is a 3D printing head, but we could also put other tool heads on it. This machine was made on another machine, a water jet cutter, with a bunch of other stock parts. And the idea was that you could bring it around and make things in the wild with it. But then I was making a lot of machines, and I wanted other people to make machines. And so I thought, how do I make it as easy as possible for other people to make machines? And not just the same machines, but different kinds of machines over and over again. And so again, together with Alon, I started working on extensible control systems for mechanical control. So instead of saying, oh, all machines are just 3 axes and we should have one controller with 3-axis control, how can you add additional controllers on a bus so that you can have machines with, I don't know, however many axes you want, with a lot of other kinds of control. And while we were doing that, with Alon and also James Coleman, we thought, what is the easiest and simplest kind of machine we could make? And so we started making these reconfigurable cardboard linear stages that could plug into each other. So here's one of them. We're using the precision of the laser cutter to be able to make a highly precise structure, which we then fold and laminate. And they can be stacked in lots of different configurations, so people can make different machines with them. And we documented it really extensively. And yeah, I don't know. I think like thousands of people made cardboard machines using this kit. Oh, really? Nice. Someone here made one. And I don't know, a lot of the machines that people were making were maybe pretty silly or kind of frivolous. Like there were a lot of machines that did things with food, like applying precision ketchup to omelets or making pancakes or things like. But this was sort of the point where I thought, okay. It should be this easy to make machines. It should be this easy to be able to control processes in different ways. But ultimately, then I thought we kind of got stuck where I'm like, okay, we're demonstrating these silly things, but actually I really want to support a more in-depth creative practice. How can we use automation for an in-depth, iterative creative practice? And so to be able to understand what people who might want to use machines needed, we studied them, the people. So for example, these are all products made by people who sell things that are made with digital fabrication, be it 3D printing or CNC milling to make molds or computer-controlled weaving. And we found that when they make tools to be able to make the things that they make, they don't actually do this whole, oh, I'm going to make a full representation of exactly what's going to come out of it. They make their own tools where they rely on ambiguous representations, things like partial prototypes, and I don't know, they kind of squint at CSV files and somehow know what's going to happen. And they don't actually design a lot in rendered CAD. Many of them design directly in machine toolpaths because the toolpath, I think this was actually made at Autodesk, this one, by Path Design. The toolpath actually matters a ton in what the final object is going to look like. This is designed with the tool step over, not with the ridges originally in mind. And so, I think that early on when I was making machines, I thought, what we're going to do is we're going to make this Star Trek replicator, and it's going to be like that. You're going to walk up to it, and you're going to say, this is what I want. But actually, making things is, and I guess you guys already know this probably, but making things is really nothing like compilation. It's this constant iterative process in which you're trying to explore what is possible, and you're trying to push the limits of the design space that you have access to. And that design space might not have been explored by anyone else yet. So we're an iterative exploration of a physical digital design space. Hannah introduced me to the hashtag plotter Twitter. Do you guys follow this hashtag? It's so great. And looking at the things that people do on plotter Twitter, or studying what they do, is they don't want these monolithic tools that are just like, yeah, make the perfect plot. I mean, that's what an inkjet printer maybe already is. Instead, they want lightweight and flexible design tools that they can do computational design and explore things like ink textures and paper textures and how things actually end up. We also study people who are using P5.js. P5.js is a programming language for making visuals. And we studied how they were also reusing each other's code on forks on openprocessing.org. And we found that unlike maybe for other code that has specific optimizable objectives, here people are really trying to explore a design space with different behaviors. They're collecting things, they're tuning variables, they're trying to extend other people's work in different ways. And that means that the kinds of tools that maybe you use for programming when you're trying to optimize for a really specific thing are not as useful when you want to do this exploratory practice. And so I guess for automation, a lot of automation is focused on high throughput or really trying to be able to optimize for cost. But for people like this, automation can actually help with a lot of the tedium of some of the things that they're programming, but maybe they don't want it to take over the expressive parts of their practice. Another thing that we found when we were studying people is that maintenance and dealing with their technology, again, you guys probably find this quite obvious, but understanding the machine itself is a big part of digital fabrication, and the maintenance practices that go into it are, really integral to being able to make things with digital fabrication. This is some of the studying of people that we do, and one of the conclusions we drew from it is we want people to make things, and to support them, we have to build legible technology that's extensible, that they can integrate existing tools with. It's not going to replace everything they already have, and it supports this expressive practice. And expressive practice might mean they're going to use it in ways you didn't expect. And so yeah, these are the priorities that we're trying to follow when we're designing systems. So here are some of the systems that we've been building. So we're really focusing not on one-off tools anymore, but toolkits that support workflows where you can go through multiple steps, perhaps, of software, hardware, and other things to be able to achieve the goals that you have or the exploration that you seek. So the first one I'll show you is Jubilee. It's an extensible machine for multi-tool fabrication developed by Sonia Vasquez. And it relies on the same kinematic coupling that was in PopFab, which it has 3 balls and then 3 slots. That gives it exactly 6 points of contact. And rigid Baji motion, you have 6 degrees of freedom, XYZ, roll, pitch, yaw. And so this is an exact constraint, which means that even though this is like 3D printed, not as robust as maybe some of the other kinematic couplings that you've seen before, it still is really precise and really accurate. We can pick up and drop off the same tool over and over again, and we'll be in the same position without having to recalibrate. And so then if we are parking tools and picking them up, and so key thing about Jubilee is it has this cable-driven preload wedge plate that allows it to pick up and drop off different tools. If we're picking up and dropping off different tools, say a microscope and a syringe, or a 3D print head and a milling head, we don't have to do different calibration steps in between, and we can start developing workflows that rely on multiple tools in one system. And a big part of what we're trying to do with this is also have other people build it. Open source hardware, often you have access to the source, but it's still centrally produced, maybe by crowd supply. Thanks, crowd supply. But for some things, if you want to customize them, then where the production happens becomes more complicated. If you want to make all of your own tools to add them to this machine, how do you support other people who maybe have never met you, who haven't seen your machine in person, who still want access to this kind of hardware? I guess the short answer there is lots and lots and lots of documentation. And so how do you make lots and lots of documentation, so not just for people just like you, but for people who maybe don't have the same expertise, who can then still join the project? So here are some of the tools that we developed for Jubilee that are specifically for laboratory automation and science workflows. This is for picking up tiny plants, and then there we have different syringes and then different imaging tools for a side and down view. Here's one where we took have any of you used the OpenTrons machine? Yeah, OpenTrons is a open source liquid handling machine, so it can pipette. So instead of manually pipetting, you can program pipetting. Anyways, they have an open source tool, and we adapted their tool head to our machine so that you can do pipetting and imaging in one work envelope. And we're also developing manipulators so we can pick up and drop off things without touching them, which is important to biologists and other laboratory scientists. We can levitate things, but we can't very reliably pick them up and drop them off. So it's a work in progress. And then the other thing that we're doing, which is different, is Jubilee runs 3D printing controller hardware. And so the logical way in which lots of people control 3D printers is with G-code, but G-code doesn't let you put in feedback loops easily. And so instead of having people generate tool paths in slicers, we're controlling our machines directly from computational notebooks. This one specifically, this one is a Jupyter notebook that allows us to set up a machine and then set up different decks. The decks, by the way, are also kinematically coupled, set up different tools, and then start doing different workflows with it, gathering data, and then perhaps having the machine do different things based on the data that you've collected. And so then you can start doing things like prototyping a feedback loop. This is one of our collaborators who does bacterial identification. Apparently, it's bad to give people just all antibiotics because that contributes to antibiotic-resistant bacteria. And so you want to figure out, okay, what are they infected with? And to do that really quickly, clinicians do a variety of different kinds of tests. And how do you make those tests faster? Well, it's going to take more time for the clinician to explain to me what they need than it might if they had toolkits like this to be able to develop their own automation workflows for doing this experiment that they're doing constantly all the time anyway. So how do we support them in prototyping feedback loops for their applications rather than us trying to say, okay, well, you need to hire an engineer for that? We've also been we've been automating growth assays for duckweed. You guys know what duckweed is? Some of you, yeah, duckweed. So we at Machine Agency think that duckweed is the model organism of the future. It is multicellular, and it is plant, but it doesn't grow in soil. So all of the annoying things that you have to do when you're doing experiments with plants, like taking them out of the soil and then replanting them and trying to distribute them, is difficult. And so duckweed, great for automation because you can pick them up and drop them off easily. And here we're doing different experiments where we're trying to vary what we feed the duckweed and how much salt they have to live in, things like that, to be able to see how they behave. Why is duckweed called a weed? I guess, if there's a lot of fertilizer, I don't know why duckweed is called a weed, but if there's a lot of fertilizer runoff in some ponds, it can kind of go crazy and then cover the whole pond and no light gets to the water below, and that can cause acidification. And I don't know, it can be bad. I don't know. We do other things. We do other things with science workflow Jubilee too. This is a Jubilee in a chemical engineering laboratory. And they're trying to discover new materials where they're trying, apparently there's a lot of different kinds of materials where they need to characterize different combinations of base materials. And so how do you support them in exploring what new materials they could make are? And here, so we're starting with experiment design and then supporting them in creating all of the samples that they do the tests with, but then also closing that feedback loop of, okay, now we have made a whole bunch of different options of samples, and based on measurements that we're taking from the samples that we've created, we're now going to say, okay, this is a promising area, and we're going to automatically start doing experiments in that, with those ratios of materials rather than trying to do a brute force exploration of the entire space, which maybe is possible if you have 3 base materials, but if you have, I don't know, like hundreds of base materials that you could be combining, then some amount of smartness perhaps is, or some amount of optimization and feedback loop is perhaps warranted. All right, so we build hardware and we build software, and software people really like abstractions, and abstractions are often really great for things. But actually, increasingly in machine agency at least, we found that some of the abstractions that people are using to be able to design different things are, I don't know, they don't allow different things. So one of the ways in which we explored this is p5.fab. It is by Blair Superraman. It is a programming language for 3D printers that uses p5.js, but it allows you to do, it allows you to do a bunch of things that 3D printers assume you don't want to do, like bridging between things, or creating huge globules, or increasing the Z as you're printing, or doing different kinds of things. And so, when do you actually want to, and it allows you to make these really, this is obviously sped up, but it's pretty fast to print this. And it allows you to print different kinds of shapes or different kinds of structures that a traditional slicer would never allow you to program. Playing around with the primitives of machine control, or saying like, I want a laser cut, and maybe I want to vary the Z as I'm going from X to Y, or as I'm varying my X, Y, I also want to vary the Z. These are things that a lot of machine control software doesn't allow you to do because of the abstractions that were designed for it. And it limits, the design space that you can explore, therefore. And so rethinking some of the abstractions that go into these tools is another thing that we're working on. We have a more complicated 3D printing library that lets you do non-planar 3D printing. Here are some non-planar printed lampshades. But the main reason that we developed this non-planar 3D printing is to develop ways of manufacturing fully interdigitated batteries or electrodes that increase the amount of contact area. And so you can't 3D print them in a planar way because it creates all of these possible shorts between the 2 interdigitated fingers. And so how can we control machines in unconventional ways, or things that in ways that people aren't currently expecting? We build a lot of software for stuff like that. And maybe other kinds of workflows like slip stitch knitting. You guys knitters, have any of you knit? Wow, very few of you knit. Well, knitting is cool, you guys. Slip stitch knitting is a way of doing color work. So this is the most common kind of color work, fair isle knitting. Maybe if you have socks with logos on them, you've seen this in your sock where you have these loops on the other side, and your toes get caught in them, and it's bad, and loops are bad, wasted yarn. And there's another way to do color work called slip stitch color work, also known as mosaic knitting, where you're pulling up stitches from previous rows. And it allows you to create textiles that don't have these loops on the back but still are using multiple colors. But it's very hard to design for because Fair Isle lets you basically design in a pixel editor, whereas this means that your operations and your colors together result in your final textile. And so Hannah Twigg-Smith, who's sitting over here, developed a representation and design tool that uses yarn topology to simulate what's going to happen when you pull up stitches from previous rows, either with tuck stitches, which is what is shown here, or with slip stitches. And so here's her interface. Here is the stitch repeat. So these are the stitches that are being repeated over and over again. And then these rows are the colors. And you can see as she's editing the stitch, as she's editing both the stitch repeat and the color rows, it's drastically changing what the simulated textile looks like. There is a spring simulation that she's applying to that yarn topology to be able to simulate what the final textile is going to look like, which allows for this rapid iteration of here is my chart, and then here's what the design looks like. And then this is the knitting machine that we brought with us. Maybe some of you saw it over there. We're teaching a workshop tomorrow where you guys can design your own knits and then knit them on the knitting machine. It goes exactly this fast. This was not sped up at all. No, just kidding. And you can see that the design tool, these are screenshots and these are photographs. And so you can see that the design tool approximates the resulting fabric really well. And it shows you all of the cool things that slip stitch colorwork does, including creating curves, which is something that you can't do when you're doing pixel edit design. And also, I don't know, you can, here's a good one to figure out how unintuitive it is. This is the chart, and this is the resulting design. So you can see the simulation helps a lot, or the simulation works really well to be able to create designs that are, to help you create designs that look like what you would want them to look like. We were using a manual knitting machine, which allows you to, as you're pulling the carriage across, really feel the tension in the yarn. And unlike fully automated knitting machines that maybe move the carriage automatically, that allows you to knit with things with extremely high tension, like enamel wire. And so here's a sample that we made where we're just doing some capacitive touch sensing. So if you wanted to design in different capacitive touch sensing patches into knits, I don't know, that's a cool application of this tool. Well, that's it. Takeaway is machines, it matters what we do with them. Again, I'm Nadya Peek. I run the group Machine Agency. We're always recruiting PhD students. If you're a PhD student, you get paid. You make stuff, it's great. If you want to know more about that, this is our website. Yeah.